Welcome to this next lecture, from the equivalent circuit we have, in my last few lectures we drew the torque slip characteristics and highlighted the importance of that, because torque slip characteristics tells you if the machine is run at a particular speed or slip, how much electromagnetic torque the motor is capable of developing. And in our last lecture, based on the equivalent circuit, we got these two very important results. One is T max, the maximum electromagnetic torque developed by the machine is V Thevenin squared by 4 pi ns. Mind you, this ns is in RPS, mechanical speed, and 1 by this is R Thevenin's plus square root of R Thevenin squared plus x Thevenin's plus x 2 dash squared. This was T max, and the slip value at which this T max occurs, I denoted it by alpha, and it was like this, R 2 dash by square root of R Thevenin squared plus x Thevenin's plus x 2 dashed whole square. So, these were very important results. Now, the typical torque slip characteristics we always draw, that will be something like this. Here it is s equal to 1, here it is s equal to 0, and speed is this way, which is nr equal to 0, and this is nr equal to ns, and this is T max, and this is the value of slip at which maximum torque occurs, and these are the expression for that. Therefore, if the equivalent circuit parameters are known, we will be able to predict what the motor, how much maximum torque the motor is capable of developing, and at what slip it does. I told you that for a very well designed motor, this alpha should be, a typical value could be 0.1, and this is 1, and this is starting torque. And then I told that if the torque slip characteristics is known, machine will operate at the point of intersection. Suppose this is the load torque, point of intersections, motor will operate. It gives two speeds, out of which one is stable, that is this one is the most important one. Machine cannot settle down at this point, although T equal to T L, because it is critically stable. A slight disturbance this way or that way will change the operating point either to this point or to this point, that is motor will not run, and it will never come back to its original position. That is why it was called unstable, so far as constant load torque is constant. And last time I told, therefore, this zone for a constant load torque like this is stable zone, and this one is unstable zone. And motor will operate primarily in this steep portion of the torque slip characteristics. And also we noted that the full load torque, if it is full load torque, it will be more or less in between, so that you keep enough margin from the line of demarcation between stable and unstable zone, and the full load slip could be of the order of 0.05, half of this is 0.05 and so on. Okay. Now, today what we will do is this, we will try to see how this top slip characteristics gets modified if I change certain parameters in the which are appearing in the equivalent circuit. For example, this is the stator of the induction motor, which is energized from 3-phase supply, and this is the rotor. I have assumed star connected for the time being, and these rotor terminals are shorted, okay, and you give 3-phase supply here, okay, and machine stator field is produced, machine runs suppose in this direction, and obviously the net field is also moving in this direction with NS, stator field or main field, whatever it is. Now, this R2 dashed and X2 dashed are the inherent resistance and leakage reactance of the rotor, R2 and X2. These are of course reflected values, it should be multiplied by a square terms, we know that. Now, and here this per phase voltage applied is V1. Now, if you change the supply voltage, how this torque slip characteristics is going to modify, let us first examine. Suppose we will vary the supply voltage, suppose V1, that is the supply voltage, is varied. Obvious reason, if V1 is the rated voltage, I am not going to increase the voltage, because it will exceed the rating of the induction motor. You know, I can only reduce the supply voltage. Therefore, V1, if it is suppose reduced, so V1 is to be reduced only, not increased, because assuming V1, this is the torque slip characteristics corresponding to rated applied voltage like this, then you will see that if V1 is decreased, that becomes meaningful. No question of increasing the supply voltage, it may exceed the rating of the, suppose 400 volt 3-phase machine, I should not go beyond 400 volt. Now, if V1 is decreased, then the question is how V Thevenin's, because V Thevenin's has got the term V1, and recall the equivalent circuit here R1 X1, which are small, and here it is Xm, and this is X2 dashed, and this is R2 dashed by S. This is the equivalent circuit. Now, here it is V1. So, I am playing with V1, I am reducing it. Then we know that V Thevenin's is nothing but the magnitude of this V Thevenin's is V1 applied voltage divided by this current, that is R1 square V Thevenin's open circuit voltage. So, R1 square, this is also J, plus X1 plus Xm whole square, is not, this will be this into Xm, that will be the magnitude of the voltage. Generally R1 X1 is small. So, this is approximately, it will be not a bad idea to understand what is going to happen if V1 is varied, to approximately tell okay, this is close to V1, because R1 x1 if you neglect, this will be under root xm, xm will cancel, it is approximately V1. So, because if R1 x1 small compared to xm. So, if that be the case, so if you reduce the voltage in this expression of T max, the T max will also get reduced, because V Thevenin square is approximately V 1 square. As a first approximation, we can assume that. Therefore, if V 1 is halved, suppose halved, that is V 1 is halved, then T max now will become that is V 1 by 2 you have made. So, it will become 1/4 T max will become 1/4 of the T max when supply voltage was equal to V 1, is not it, maximum torque will become 1/4. If you make it 1/3, it will become 1/9, because square of the voltage, supply voltage dictates what should be this T max. Therefore, if this is the T max for applied voltage V 1, if you have reduced the voltage by half, your torque slip characteristics will become like this. This one will become 1/4 that of this. Slip at which maximum torque occurs, that does not change. Therefore, this peak here will remain same, alpha value remains same, but it will become only 1/4. And therefore, under an applied voltage which is equal to half the rated voltage, and suppose this is the full load torque of the machine, you can easily see you cannot supply a full load torque, because machine is not at all capable of developing TL in its range of 0 to 1. So, the effect of variation of supply voltage reduces T max drastically. If the supply voltage is made half, it becomes 1/4 and so on. Therefore, this is how the torque slip characteristics will get modified for different voltage. If you reduce it like this, so this is V 1 decreasing, V 1 decreasing, a family of curves you can get. Keeping frequency constant, frequency, supply frequency I am not going to change, and I have assumed you do not have any provision to vary the frequency. Therefore, this is the effect of variation of supply voltage on torque slip characteristics. Therefore, with applied voltage less, you can supply a load torque which should be below this T max and half of this. So, the operating slip here will be like this, and full load torque maybe, which should be also drastically reduced. You cannot connect a mechanical load which demands a load torque whose value is greater than T max now, that is this one. So, a machine will looks like will underperform. We will come to this point later when we talk about speed control of the induction motor. So, this is the effect of variation of supply voltage on the torque slip characteristics. Now, there is another parameter which we can vary, and see what is going to happen. Before that, one problem I will try to just mention, and this is like this. See, this is the torque slip characteristics I told you. This is S equal to 1, S equal to 0, and this is suppose the full load torque, as I told you like this. T load is equal to T full load, suppose, somewhat midway. Now, you can see if the motor, one way to supply this full load torque is that with the load torque present already on the shaft of the machine and machine is stationary, if you switch on the supply, your starting torque is only this much. Machine can develop and opposing torque is this much. Therefore, motor will fail to start, because you have not produced enough starting torque to overcome the opposing full load torque which is already present. Okay? Therefore, this machine cannot be started as it is with full load mechanical torque connected to the shaft. So, what is the way out? One way out is that do not connect the mechanical load first, then the machine has to start only against the frictional torque, which it can do. Frictional torque may be within this limit, and then machine will settle down to no load speed, and then you connect your mechanical load torque, then the operating point will shift here and settle down here, which is the stable zone. But sometimes what is needed is that the machine has to start, this mechanical load will be permanently connected whether it is running or not, and you switch on the supply and machine should be able to supply this full load torque. That is the thing required. But then we are facing this problem that okay, starting torque is only this much, what can we do? There is a way out. What is that? And that is a very nice thing. We have seen that these two relations are very important. Okay? What is R2 dashed? R2 dashed is the rotor circuit resistance, and here I have shorted the rotor. So, this small R2 is the inherent value of the rotor resistance per phase. Now, if we could, the idea is at the time of starting I will connect some resistance in the rotor circuit, because rotor terminals are available. I will connect some resistance in the rotor circuit at the time of starting. Therefore, I am essentially trying to understand how the torque slip characteristics will get modified if I vary the rotor resistance. How I am varying? The inherent rotor resistance, this R2. Now, I will connect some R2 external. So, total rotor resistance will become this R2 plus R2 external per phase in the rotor circuit. And this R2 plus R2 external dashed, then I have to substitute in the expression of the electromagnetic torque as well as in the value of the slip at which maximum torque occurs. So, you see this is the thing. So, this is the torque slip characteristics with inherent resistance R2. Now, I will increase the rotor resistance by connecting some external resistance of equal values in each of the phase hairs, and then I will short. So, if R2 is increased, if R2 is increased by adding extra resistance in the rotor circuit, then how the torque slip characteristics gets modified. That is the question we are asking ourselves. Now, the value of this slip T max, if you look at the expression, does it depend on R2? No. R Thevenin's has to do something with R1 and Xm. B Thevenin's is supply voltage constant, there is no R2 dashed. So, T max value is not going to change. What is going to change is the slip at which maximum torque occurs. Note, if you increase R2 by connecting external resistance, say R2 external, I will say T max does not change, T max does not change. But this slip at which T max occurs, that changes. That is, alpha changes. And alpha becomes more now, alpha becomes more compared to the rated condition, this alpha. This is the alpha with inherent rotor resistance per phase. Therefore, the shape of the curve will not change, because some parameters we have increased a bit resistance. Therefore, what will happen if you add some external resistance, what I am telling, this T max is fixed, it is not going to change. But the value of alpha at which maximum torque, it will be alpha nu will be R2 plus R2 external dashed, okay, R2 dashed plus R2 external dashed divided by blah blah, I mean that thing, square root of R Thevenin square plus X Thevenin's plus X2 dash squared. This will be the value of alpha nu. So, and this will be greater than alpha, which was, what was alpha? Alpha earlier was based on, alpha was simply R2 dashed by the same square root, I mean whatever it is, but only numerator was R2 dashed. Therefore, this alpha was less and it will then becomes something like this. This one is, this is for R2 dashed, this is for R2 plus R2 external. So, the slip at which maximum torque occurs now will become alpha 1. Now, if you observe carefully, by doing this, the starting torque has been increased. Earlier it was this much, but now it is this much. But still it is less than that opposing full load torque. So, therefore, we will be tempted, and rightly so, because of the fact that alpha shifts to the right and then further increase R2 external, then you will get a torque like this. So, R2 external increasing this way, I will write it like this, to external. If you further increase, it will maximum torque will occur at some value of alpha 2. And you now find that by incorporating an external resistance in the rotor circuit, the starting torque has now become greater than the load torque. And if you now switch on the supply with the opposing torque present, then machine will start, no problem. And machine will start and will settle down at this point, because this is the load torque characteristics with some R2 external present, and machine will run at this speed, because that is the stable zone, only one point of intersection we are getting. In fact, if you wish, you can connect a judicious value of R2 external so as to get the starting torque equal to the maximum torque the motor can develop, because I will then connect there exists some value of R2 external such that this T max, which does not change as you vary R2, T max may occur here at s equal to 1. So, that machine will accelerate fast. Therefore, not only that, this problem that with inherent rotor resistance, although the machine is capable of starting where against full load torque, one way out is do not connect that full load opposing torque at the beginning, do not do anything with the rotor, keep it shorted right at its terminals, and then after machine settles down to no load speed, put that opposing load torque on the shaft, and then machine will operate here. But I am now telling another interesting thing. If the rotor terminals are available, I will connect some R2 external in this green resistance, external resistance, equal values, so that balanced thing is preserved. So, per phase resistance will be R2 plus R2 external, and I will switch on the stator supply. But which torque slip characteristics it will follow? If you have added enough rotor resistance such that it is modified here, then machine will accelerate fast and operating point will shift, and this is the point of intersection, this load torque is present, it will run at this speed, is not. Now, the big question is whether after getting that starting torque advantage, should we keep this resistance intact in the circuit? The answer is obviously no, because of the fact if you keep the resistance in the circuit permanently after exploiting the starting torque advantage, that particular property, rotor resistance will be R2 plus R2 external, and the power loss in the rotor circuit will be then more while supplying the full load torque. Efficiency of the motor will reduce. Therefore, it is better you connect some selected value of R2 external and then as the motor picks up speed, you gradually cut out the resistance. Finally, this rotor circuit should be shorted. We will discuss it further in the next class.